immunization. Okay? And this is where we can utilize our immune system and our immune system's memory response to help prevent infection altogether. Okay? Now, this can occur in both an active and a passive way. Active immunization is where you actively produce memory cells. Okay? So the whole process we just talked about from start to finish, that is what occurs during an active immunization. Okay? You're being exposed to antigen, it's being processed, presented, T cells and B cells become activated, you get memory cells, and now you're protected from that antigen. Okay? This can both happen naturally or artificially. Naturally is where you actively get infected, right? So if I get the flu, that is a form of natural immunization. Right? My body is responding to the flu, I will produce memory cells, and now I'm protected from that particular type of flu. But this can also happen artificially. This is where I take flu, I kill it, and I inject it into your arm. A flu shot. It's a way for you to get memory and a response, but it doesn't actively make you sick. Passive immunization. This is where you do not produce your own memory cells. Instead, you take antibodies and you use them from somewhere else. Okay? So maybe from mom, okay, in the form of colostrum or from a placenta. Or you take them from an animal like a horse and inject them into someone, and that helps clear the pathogen. Okay? The beauty of passive immunization is that it's very, very quick. Matter of minutes, it starts to work. Okay? So if you're dealing with a toxin or a venom, this is the best approach because those will kill you very quickly. Okay? But it is very short term. It only lasts for a couple days. After that, it's completely gone and you have no memory. So if you get injected with the same toxin or the same venom, it will give you the same kind of response, okay, of death. Now this can also occur naturally and artificially. So natural, as I mentioned before, is getting it from mom through breast milk or placenta. Artificial is from a horse, right, or from another animal. So again, natural, active natural is being exposed to pathogen and getting sick. Passive natural is getting it from mom, right, from her breast milk or from her placenta. Artificial, so active artificial is vaccination. So where we take the pathogen, we inject it into you. It's not enough for you to get sick, but it's enough to give you a memory response. Passive artificial immunization is where we take antibodies that are preformed from another animal, and we inject it into you, giving you quick protection, but there is no immunological memory. This is what they all look like, in case you're wondering what breastfeeding looks like. There it is. Antitoxins. So antitoxins, also known as antivenoms, these are a form of passive immunization. Okay? This is where most passive immunizations get used. So as I said, toxins and venoms in general can be very potent. They can cause very rapid responses in the body, which can quickly result in death. So you don't have enough time to wait for your memory cells and all that response to develop. Okay? So instead what you do is you take a little bit of the toxin, inject it into a horse, not enough to kill it, but enough for the horse to develop a response to it. You then bleed the horse, pull out those antibodies, and inject it into a person. Those antibodies go in, they bind all that toxin or venom, precipitating it out, neutralizing it, and preventing it from killing you. Okay? But again, you get no long-term protection. So that's how antitoxins and venoms work. Now let's talk about how the vast majority of our vaccines work. Okay? Most of our vaccines are going to be active in nature, okay? Which means you produce your own immune response to them, you get your own memory cells, and thus you are protected for very long periods of time, sometimes for the rest of your life. Okay? Now for this to work, there's a couple things we have to think about before we design the vaccine. First of all, we have to think about the antigens and what antigens are going to work to protect the person the best. Okay? Not all antigens work well. Okay? So you really have to think about that sometimes. Obviously, you want it to be effective. If it's not effective, there's no point in utilizing it. Okay? And for vaccines to be effective, we usually like them to be about 80% effective or better. Which means 80% of people that get the vaccine are protected from that particular pathogen. Most of the vaccines we administer in the United States are even higher than that. So MMR, for example, is like 99% effective. 99% of people that get it are protected from measles, mumps, and rubella. It should be easy to administer. This is usually through an intramuscular injection. It should be safe, where it doesn't cause deaths or other problems. And it should be relatively cheap, and that's because these are often done on very large scales, usually using the government. Okay? And that's because for vaccines to work, you need to vaccinate the majority of the population. Now, when we look at active vaccines, there's basically two main groups. Okay? Whole cell or virus vaccine, or a subunit or what we call engineered vaccines. Okay? Historically, and probably the most important, the one we use the most, are going to be these whole cell vaccines. This is where you take the whole cell, if it's a bacteria, or the whole virus, it's a virus, and you inject it into something. Okay? Now, this can be alive. Okay? However, it's not pathogenic. We usually attenuate it or manipulate it so it's no longer causing disease, but there's still the antigens present, so you develop an immune response. Or it can be killed, which means it's the pathogen, but we kill it with formaldehyde and then inject it into you. Okay? That way there's no potential for it to cause disease, but you still get an immune response to it. Subunit vaccines, this is where instead of taking the whole virus, the whole cell, we only take the antigens. So we take the antigens as DNA, put them into bacteria. The bacteria then make the actual antigenic proteins. We purify those, and then we inject those into the person. These are relatively new. Some examples of antigenic vaccines are the HPV vaccine, hepatitis B vaccine. Okay? And these work pretty well. However, they're not as good as these guys. Okay? It's the whole cell. And this is why both of those require boosters. Right? You need to keep getting them again and again, usually 2 to 3 times, until you produce enough antibodies. And it's because they're subunit and they don't give you the best immune response. So, when we're developing our whole cell or viral vaccines, because these are the most common, how do we determine whether we want it to be alive or dead? Okay? And the answer is it really just depends on the organism. Obviously, if you're dealing with dead organisms, this is going to be the safest. If it's dead, there's no way it's going to cause disease in you. Okay? There's no way it can become pathogenic. It's dead. But the problem with dead organisms is they often go into the body in the wrong way. Okay? So an example would be the flu vaccine. The normal flu vaccine most of us get is the one that is given as an intramuscular injection. Now what that means is most of your protection to the flu, in that case, is going to be right here in your arm. Why? Because that's where it's the most concentrated, right? Where do we get flu? I don't know about you, but I get it up here, okay? So it doesn't give you the best response. And you may say, well then why do we stick it in the arm? Well, if I were to take dead flu virus and shove it up your nose, absolutely nothing would happen. You would just sneeze it out. Why? Because it's dead. It's not going to give you an immune response. Okay? But if you take a needle and jab it in your arm, what do you get? Inflammation. And so the inflammation recruits immune cells, and they go, oh, I don't really see anything except this dead crap. Well, let's just look at it anyways. And that elicits an immune response. Okay? That's why it gets sore after the injection. That's why you get a little warm, a little fever sometimes. Live organisms obviously are going to give you a better response, because you can inject them right into the site of infection. So flu mist is a live attenuated flu vaccine. You shoot it up your nose, and this protects you in your upper respiratory tract, where you're probably going to get flu. Okay? But the problem with this is that sometimes you get the flu just from the vaccine. It's attenuated, it's not supposed to be pathogenic, but shit happens. Okay? And sometimes you will get the flu from it. Now, you will never get the flu from the dead guy, the one that's injected in your arm. I don't know how many times I've heard people ask me this question, how come I get the flu every time I get the flu vaccine? You are not getting the flu. What you are getting is just a reaction to the injection and the immune response. Okay? But it is not the flu, unless you got the flu in your arm, which I've never heard of. All right, so up at the top, this is our whole or viral vaccines, okay? Again, you can use a dead vaccine or an attenuated vaccine, okay? It really just depends on whether or not you want it to be super safe or whether or not you want to get the best responses, okay? Ultimately, this usually depends on how virulent the pathogen is. For flu, if it's not that virulent, because most of the time flu isn't, it's not that big of a deal if a couple people get the flu from it, right? It's usually not going to be that big of a problem, at least in a healthy person. However, for Ebola, you probably don't want to use one that's going to give 1 out of 1,000 people Ebola, right? That's probably not the right way to go. So then you would use the dead vaccine. Subunit vaccines, this is where we just express the antigens, usually in bacteria, purify them, and inject them into a patient. These don't work very well because they're not the real thing, right? It's just the little bits and pieces. They don't get phagocytosed as well. They don't get presented as well. And so you get a weaker response. Now, as you all know, we have a lot of vaccines available to us, okay? They help prevent us from getting many, many really nasty kind of pathogens, right? Measles, mumps, rubella, polio, hepatitis, the list goes on, okay? However, there are still a lot of pathogens that we do not have vaccines for, okay? And the reason for that is because they're the difficult ones. If they were easy like all the other guys, we would have a vaccine to them. And they are difficult because they like to change the way that they look all the time. So HIV is a primary example of this. So if I get HIV, my body develops an immune response, I make antibodies, and that blocks that HIV at the time. Well, what does HIV do to get rid of it? They just change the way they look a little bit, and now those antibodies no longer are effective, and now my immune system has to develop another immune response. And then HIV just changes itself again and again and again, and so your immune system never clears it. And so obviously designing a vaccine to HIV then becomes difficult, right? You can't just take dead HIV particles, inject it into you, and say you're protected, because there's so many other flavors of HIV that look totally different than that you can still get infected with, okay? So for that, we kind of had to think outside of the box and come up with different ways to develop vaccines, okay? And this is where we really get into genetic engineering, okay? Or recombinant DNA technology. So the most common genetically engineered vaccine is a Trojan horse vaccine, okay? This is where we take a virus that is pretty harmless to humans, we pull out all of its bits and pieces, and we put in antigens that we want to protect you against into. We then inject that inside of you, that infects some cells, it gets a good antigen response, and then hopefully you clear the pathogen. Okay? Now this has been tried many times with HIV, and every time it has failed. Okay? And the reason for that is the parts of HIV that do not change, that we can use antibodies against to protect you, are very, very difficult to get to, okay, by the immune system. So even if we develop vaccines that produce that kind of response, that oftentimes don't work. Okay? So we are still trying things, we are still trying to make this work. However, it is more problematic than we thought. The other approach is, instead of using a virus, is to use DNA, naked DNA. In this case, we take plasmid, much like the one you guys used in the P-glow experiment during the transformation. We make a big batch of it, purify it, and then inject it straight into you. Okay? This then magically incorporates itself into cells. I say magically because we don't really know how it happens. And then once it gets in, the cell then transcribes, translates that plasmid. This then expresses the antigen on the surface, and your immune system can then come and respond. Okay? People used to think this was a pretty good idea and something we could really exploit, but it hasn't really taken off yet, and that's because we don't really know what's happening. Right? We don't really know how it's working. And sometimes, for some individuals, these plasmids will get in a lot of cells, and these cells will then get killed by the immune system because they're expressing the antigen. And this can then cause tissue problems in them. So it's not really there yet, but it is something we are thinking about and potentially exploring. So, how are vaccines administered and what are the potential side effects? So as I said, most vaccines are going to be given as an injection, usually as an intramuscular injection. That is going to give you your best immune response for the dead vaccines, okay, the dead organisms. There are some oral vaccines available, okay, but these are limited, and they're usually only for fecal-oral route transmitted organisms, like polio, for example. Okay? That's because if I were to give you, dead influenza and you swallowed it, it would give you a nice influenza response in your gut, but that would do absolutely nothing for your influenza, okay? Because influenza is in the respiratory system. So most oral vaccines are only for GI bugs. Now in vaccines, we often add in additives known as adjuvants. And adjuvants are compounds that stimulate a stronger immune response, okay? These are often metallic compounds. They're usually silver or aluminum based. And they make the immune system response much stronger in the area. Okay? They're harmless. They relatively cause few problems. If they were to cause a problem, it would be a low-grade fever, okay? Or maybe an allergy if you're allergic to metal. Other than that, not that big of a deal. Now there are other things sometimes found in vaccines, like preservatives, which prevent fungal and bacterial growth. These are important because if you have fungus or bacteria growing in your vaccine and then you inject it into someone, you've just infected them with fungus or bacteria, and that could cause a lot of problems. Okay? Traditionally, one of the preservatives was Thermosil, which is a mercuric compound, just made from mercury. And it got a lot of bad rap about it because there was a guy in the UK who published a flawed study that showed Thermosil caused autism. However, later on we found he completely fabricated the data and made it up. Okay? But there are still a lot of people that believe this, and this is why you hear of people not vaccinating their children, because they're worried about Thermosil. Well, the good news is that most vaccines have very, very little Thermosil or no Thermosil at all. So even if you're worried about that, I wouldn't think twice about using it. Now, there are side effects associated with vaccines, but most of these are going to be very mild. The most serious side effect with vaccines is usually an allergic reaction, okay? And that's because some of the compounds in vaccines can be allergens, and if you are allergic to that, and then we just inject a concentrated form of it into your arm, you can go into shock. Where this becomes most problematic is with the flu vaccine, and that's because the flu vaccine is made in eggs. So if you happen to have a chicken or an egg allergy, you may get a strong allergic response to it. Okay? But generally speaking, most of the time we use things that aren't serious allergens. So who, why, and when do we vaccinate? Okay? Now vaccination is designed to protect an individual from getting infection, okay? Which is great for you. But if you do it right, you can actually protect the entire population, even people that aren't vaccinated, okay? This is a concept called herd immunity. What this basically states is if you vaccinate the majority, you protect the minority. And this becomes really important when you're dealing with the minority, which are usually young infants or babies that cannot be vaccinated because they are too little. Okay? So in general, we vaccinate the majority to protect those people who cannot be vaccinated for whatever reason. Now, the way that this works is if I vaccinate, let's say, 90% of this room, okay, and let's just say to measles, mumps, rubella, okay, what that means is 90% of you can't get MMR. And because 90% of you can't get it, the 10% that are left are less likely to develop it because the virus can't spread throughout the population easily, right? Because there's that 90% blockade, okay? Now, the amount of people you need to vaccinate does differ depending on the agent. So for measles, for example, because it's super, super infectious, you only need one particle and can easily be transmitted, you need about 99% of the population vaccinated. But then for other things like influenza, for example, you get about 80%, then you get a pretty good protection. Okay? It slows down the rate very dramatically. Okay? So it really just depends on the pathogen itself and how readily it can be spread. So here's a list of the vaccines that are required in the United States. You can see most of these are given from about 1 month of age to about 4 to 6 years of age. Okay? Most of these are to pathogens that are either really nasty to get or deadly, especially in young children. So I always get people that ask me, well, why do we give so many of them, within the first 6 months of a child's life? Can't we wait? You could, but if they were to develop these, they would probably die at that age. Okay? So giving it as soon as possible is what protects them from this death. Now later on, you can also get vaccines, but most of these are going to be booster-like vaccines. Okay? So ones you get again after your initial vaccine to really make sure that you have the protection that you need and to prevent that infection later on in life. And that is it for chapter 15. Any questions?